Thank you very much, Lynn, for your kind introduction. I'm supposed to talk about the vasculature in above ground and below ground stems. So my talk is structured into 5 parts. One is reservations against the use of the term atactostele, difference between above ground and below ground monocot stems, where is vasculature formed, reasons for vasculature modifications, and finally, summary. So, reservations against the use of the term atactostele. Back in 1982, already stated the textbook concept of the monocotylous vascular system as an atactostele, that is, a system of randomly scattered bundles, is misleading and inaccurate. Second, Tomlinson, 2006. Our understanding of the vascular system of monocots has advanced to the extent that we can abandon its meaningless description as an atactostele or as consisting of scattered vascular bundles. Third, I think the name atactostele already contains the problem. It says it means disorderly or irregular. And this is something I will show is misleading. So when we look at a transverse section of Johnson grass, Sorghum halepense, a culm and a rhizome, we get the impression that the vascular bundles are randomly distributed over the section. And Johnson grass actually might serve as an example for scattered bundles in culms and rhizomes. You see something similar with itch grass, which I think grows in this country, Rotboelia, and maize looks similar. So when you look at other species, like blackgrass, which grows in Europe, and quackgrass, you see that the bundles are arranged almost ring-like at the periphery, and in quackgrass, it's almost the same. So bundles are not scattered over the section. And as Lynn already stressed, many culms are hollow. So let's look into the internode of quackgrass more in detail. So this is an increased, a magnified part of this part. And you see a sclerenchyma outside, small peripheral bundles. You see larger bundles here. And you don't see a clear border between a vascular bundle cylinder and the cortex. So some authors call this conjunctive tissue, therefore. So small peripheral sclerenchyma bundles, larger bundles following towards the inside. And now we come to the rhizome. And this looks quite different. You have a sclerenchyma ring towards the center. You have an endodermis, clearly separating cortex and a vascular bundle cylinder. And you have the vascular bundles distributed almost in a circle. So when comparing the above ground culm and the rhizome, you see that this sclerenchyma layer is more or less shifted, but in addition you have the endodermis. And here you have a conjunctive tissue, and here you can talk about a cortex. So in many underground rhizomes, you see a clear distinction between cortex and bundle cylinder, but usually not in stems. So let's look at another group. I took examples by chance, so it takes a book to cover all this, but to exemplify it, I took a few selected families, and I took sedges, and when you look at the stems, the columns of sedges, you see they are triangular, and the vascular bundles are at the periphery, more pronounced here and more pronounced here. And the bundles are peripheral, and I will show this more in detail. They are collateral and not scattered. So, calyx acuta, here's the column, and here is the rhizome. The column is triangular, the rhizome is round. The rhizome has a clear central vascular bundle cylinder. There are cortical bundles, I will show that later on, more in detail. And so this is the calyx acuta rhizome. And what you see in magnification is the vascular bundle cylinder is surrounded by an endodermis. In addition, in the column, you find collateral bundles with the phloem showing to the outside and the xylem to the inside. And in the rhizome, you have amphivasal bundles. So phloem surrounded by xylem. Where is vasculature formed or modified? Of course, in the apex. This is arundodonax. And what you see is provascular strands and newly formed vascular bundles. And the bundle pattern in monocot stems is strongly driven by the arrangement of leaves. So it's not by chance or arbitrarily or scattered or whatsoever. The pattern follows the formation of leaves. And this cannot be regarded as irregular. So we have seen the apex is one part of the plant where bundles are formed. Then there is another part shown by Noah before. That is the horizontal Plexus strand here in barnyard grass. And this is a place of bundle formation. And this is a place of bundle modification. So the node has much to do with bundle modifications. And I show you now Phragmites australis bundles in the nodal area forming so-called glomeruli. In former times, glomeruli were known from Dioscorea species. Then a predecessor of Linnea in Hamburg, Professor Liese, found glomeruli in bamboos. And by chance, I found that glomeruli exist also in Phragmites australis. And this is unmodified phloem, and these are glomeruli. So it's some kind of modification of phloem within the node. A third part that contributes to the vascularization are buds. So you see every bud tries to connect with the stem and has an impact on the vasculature. So on top, you find roots at nodes, primarily at basal nodes. And these roots find connection with the plexus of the node. So bundle patterns within nodes differ considerably from those in internodes. The variability of nodal bundle patterns between monocot species can be high. Why do we see differences between above ground and below ground stems? One reason is below ground stems have scales instead of fully developed leaves with simpler vascularization. In rhizomes, you find roots along the whole stem, but not along the whole ground stem. And one thing is clear, upright aerial columns prone to physical stress demand other construction principles than horizontal underground structures. So these are the scales of Johnson grass, Sorghum halepense. And these are rhizomes of quack grass with roots at each node. And these are the scale leaves of quack grass. And on top of all these rhizomes, you find very different stem modifications in the ground, like corms, like tubers, like tubers here in Dioscorea or in cypress species, which show a completely different bundle pattern compared with above ground systems. So in summary, the great variability of monocot shoot structures makes it difficult to accept one single stele type as characteristic of all monocot species. So the vascularization of above and below ground stems differs considerably. Bundle types may differ, collateral versus amphivasal. Stem forms can be different, triangular versus round. Barriers between cortex and bundle cylinder are variable. And I think it takes a new and much more differentiated terminology to characterize vascular bundle systems in monocots. You will sooner or later see a book called Rhizomes, Hidden Stems with Unknown Diversity, published by Wiley. It's about to be published in August or September. So, thank you for your attention. I hope I have kept my time. Good.
Thank you very much for your talk. Question time.
Wonderful.
Thank you very much for your talk. I'm curious about the presence of the endodermis in rhizomes of, I guess, not just monocotyledons, but my understanding is that the endodermis occurs in roots because of, to regulate the absorption of solutes, right, basically to the vascular cylinder. But my assumption was always that rhizomes themselves are not that active in absorption, but the roots are, that the roots that they themselves produce. So the endodermis must be there for some reason, right?
Yep.
So that's my question.
Excellent. Perfect question. When I started dealing with rhizomes and with stems, I didn't accept the existence of an endodermis in stems. And especially in above ground stems, I'm still hesitant to call the structure endodermis. But what we see in some aquatic species is a structure with a clear Casparian strip producing the U-shape subarachne layers and the lignification, it's absolutely the same thing as you find it in roots. So I'm a fan of Catherine Esar. And Catherine says an endodermis is unilayered, uniseriate, it's complete, and it has a Casparian strip. And so the endodermis function leads people to apply this term to all kinds of sheaths. Like the mestome sheath in leaves, I still have some time, is it true?
A lot of time.
I'm giving a lecture now, sorry. So the mestome sheath in leaf bundles can look like an endodermis, but its relative position and the way it is formed is completely different compared with a root endodermis or with something in a stem. When it comes to the pericycle, the endodermis is defined as the most inner cortex layer. So when it comes to the pericycle, I could talk for 2 more hours about the use and misuse of the term pericycle, but I will discuss this in detail in the new book we're publishing together. Thank you for your question. Good question.
Any other question?
Thank you. Really nice talk, highlighting the diversity of anatomy in monocots. I'm just wondering if for your book, are you only focusing on rhizomes, or will you be covering other underground stems like the stems and bulbs or corms?
I will talk about all kinds of underground systems, and to be honest, it's not easy to differentiate between a rhizome, a runner, a stolon, and we try to start our book right away with clear definitions. People may disagree with our definitions, but if you don't do it, you leave a complete mess. And I have to admit, most definitions define rhizomes as underground systems, but there are few plant species which produce systems which are called rhizomes. Some species, most abundant in your country, have above ground rhizomes, and by chance they were called rhizomes, so for convenience, I keep the definition or define them as rhizomes. But in principle, the modifications you find in underground rhizomes are very specific. Does it answer your question? Good.
Other question?
Fine.
Thank you, Hans.
You're welcome.